We'll wait about 2 more minutes for people to come by. First, let me find out who's here. Everybody who's come by, there's 4 handouts, so there should be 4 handouts in front for you to collect if you didn't collect already. If you're not taking the course for credit, raise your hand. Okay. If you're a 3rd year CS student, raise your hand. If you're a 4th year CS student, raise your hand. Okay. Anybody else who I haven't asked and who's not an MSc, ML, or CSML student, raise your hand. Of these people who are raising your hand, are you all PhD students, or is there one of you who's not a PhD student? What? PhD, okay. Let me tell you a little bit about this course and the context in which it lives. This course is somewhat of a basic skills course for the MSc, ML, and CSML degrees. So these are kind of a wish list of things that we don't expect you to know, but many of you will know some part of these applying for your degree. And in this class, we kind of hope to reinforce those skills, even though we hope to perhaps teach you a little bit of things new. That's one part of it. The course is designed, in some sense, to complement the supervised learning course. So if you're, for instance, a 3rd year or 4th year undergraduate student and not taking the supervised learning course, you may find we don't make it a prerequisite for the course, because you may come in with different skills, but you may find things difficult in this course. The course is 100% coursework, so there's no exam. The coursework kind of falls into two categories. One part of the basic skills is some people come into these MSCs with no background or very little background in programming. So we teach Matlab, which is used in many of the courses in the machine learning and CSML MSCs, and we also teach Mathematica. If you already program, you will find these tutorials slow and a little bit boring, perhaps, because I suspect you can more rapidly pick things up on your own. On the other hand, if, for instance, you're a third year or fourth year undergraduate student taking this class and not taking the supervised learning course, you may find the coursework very challenging. It's not to say that third and fourth year students don't do these coursework successfully, but the material, the background material on the coursework is really only rounded out in a supervised learning course or perhaps some other place where you have some form of data analysis background. So the 5 courseworks, which I will give, will all be about programming various machine learning algorithms and also kind of asking hard questions. Not so many hard questions, but a few hard questions here and there, thinking about what these machine learning algorithms do. I will not teach you these algorithms. I'll give you a light overview. Some of these things you can pick up on the internet or you can pick up from other reading, but it's helpful if you're taking supervised learning at the same time. So this is my advice there. Okay. So, well, let me go through the classes. So we're going to have essentially 5 classes on Matlab and Mathematica. And I'll present the 5 courseworks over that period of time. Maxie will present some review mathematics and mathematics applied to machine learning classes, and he will set 1 or 2 courseworks on his half of the material. So there's a lot of coursework associated with the course, which is necessary if you're going to have 100% coursework. The way things are going to work today is, well, I'll try to give you this general overview of the class, but shortly we'll move into the labs. When we move into the lab, there's essentially 2 options. One, the lab is kind of split into 2. Hopefully we can fit everybody within 2 labs. I think we might just fit. In these 2 labs, you'll either be doing the tutorial for Matlab, or for those of you who already perhaps know some Matlab or quite confident in your programming skills and just want to work directly, you can work directly on the courseworks, and the TAs are there to answer questions on the coursework too. Okay? So, you know, if the lecture is too slow, if you don't want to be told what an array is, I encourage you to go ahead and take a look at the coursework. Okay, what other comments do I have? Okay. Course notes will be found on my homepage and on Massimiliano Pontil's webpage. There's a link to those pages, as well as a link to a support email class on the Moodle group for this class. Everybody who's enrolled in the class should get automatically added to the class. Otherwise, the enrollment key is just capital R, capital M. Okay, any questions about the structure or the format of the class? Okay, if there's no questions about the structure or the format, let me start discussing the homework, and then we'll move into the lab. Okay, first general comment about the coursework. If you note, there's quite a late due date for this coursework. 30th of November, okay? But there's 5 courseworks of my side, and Massey will be assigning 1 or 2. Have gone back and forth between having courseworks due in the next week or in 2 weeks, or just having them all due in a batch. There's trade-offs from both perspectives. Right now, what I think has been slightly more successful is to make them due in the batch. But this means you do have to manage your time. If you wait till the week of November 23rd, you will probably find that there's too much coursework to successfully complete. So the aim would be to try to start on these courseworks as soon as possible, otherwise things will build up. Okay. So let me make a few comments about what coursework 1 is about. So I don't know about you, but we had a pretty nice summer, okay? But between yesterday and today, all the rain yesterday is kind of cold. I feel a certain chill in the wind, and when I feel the chill in the wind, I'm kind of sad. I'm kind of unhappy. I am. But then I think to myself that happiness is still possible, because what does this chill in the wind mean? It means soon pretty little snowflakes will be coming down. And when pretty little snowflakes are coming down, I think, ooh, skiing. Skiing season is coming up. I know you're all too busy to go skiing, and I'm sorry, but I think about skiing a little bit. And I worry that you guys will have so much homework that you won't be able to ski at all. But, being the thoughtful person I am, we have this coursework which will make you think of skiing, okay? So you can experience virtual skiing in your coursework, okay? The first coursework is about a classical technique in machine learning and all over science, which is gradient descent. So in machine learning broadly, it's very common to have a machine learning algorithm where somewhere at the core of the algorithm is some optimization problem, i.e. you want to maximize likelihood, you want to minimize energy, you want to minimize cut size. There's all sorts of machine learning problems where you have some algorithm which is defined by some sort of set of equations where your aim is to find some minimal quantity or maximize some quantity. The area studying such problems is optimization, and machine learning applies such algorithms. Now there's many techniques for optimization, but perhaps when you have a smooth function defined everywhere, one of the simplest techniques is gradient descent, which can really be applied to a range of problems, and there's many ways to improve it. But this first coursework, there's a couple of harder questions, but it's really to, just to get you used to Matlab, in addition to the lab. And gradient descent, skiing, it's almost the same thing. because when machine learning, you have these problems where you need to minimize the energy. What do you think about? Well, often, what is this energy that you're minimizing? Maybe you have a neural network and you have weights that you need to train and set, and you want to get these weights to, for instance, minimum error. Well, normally you can think of the weights or whatever your parameters of the problem as being spread out over in some space. And if they're spread out over in this space, the values that a given parameter takes at some point, you can imagine as a surface above this space. So typically you have some surface, maybe it's a beautiful convex ball, maybe it's slightly more complicated, but if you're trying to, for instance, minimize, one thing you can do is start at some arbitrary point on that surface, and just like when you go skiing, you ski down, i.e., you stand someplace. This isn't exactly how you ski, but bear with me. You know, I'm not that great a skier. It's maybe how I ski. But you find the direction of steepest descent. You take a little step in that direction. Then you say, okay, what's the direction of steepest descent? Oh, it's this way. Take another step, and so forth. Now, if your steps aren't too big, for instance, you'll eventually take enough steps, and you'll, under some sort of regularity conditions, you'll make it to some minimal point or valley. So, in this first exercise, I'm going to just ask you to do a little bit with gradient descent. So if you look at the handout, you'll see there's a box. The box is the gradient descent method, and this is exactly what I've just described. So x0 is the point where you start out skiing. Lambda is how big a ski step you're going to take each time. And then the algorithm is, well, your new position in this landscape is your old position minus lambda, which is your step size, the gradient, which points in the direction of steepest ascent. And so you want to descend, so you go in the direction of steepest descent. And then, how long do you do this? Well, you need some sort of stalking criteria. Maybe you have a certain number of steps. Maybe your solution isn't changing so much. This is what you will do. Okay. Let me go through all the exercises. So this is what we're studying. The first exercise, problem 1. Well, you start out, and I basically ask you to plot what's in figure 1. Often this question involves asking a question because it seems too easy. Well, it is as easy as it seems. Basically, I just want you to produce this plot, okay? And I think I put the commands down to produce this plot. So there's a hint. Then I include a piece of code in the directory. If you look at the top of the assignment, I give my website, then I give the course title, and then if you click on say week 1, there'll be sample files. And in the sample files for week 1, you'll, for instance, find this function gradient descent written in Matlab for you. FC and DFC are 2 functions which I've also included in the sample files. Where FC is the function that you're optimizing and DFC is the gradient. So I ask you to visualize this in 3 dimensions. Make your visualization as smooth and as pretty as possible. In these courseworks, please write up your coursework clearly. Presentation is taken into account for the final grade. Figure 3, so what's figure 2? Figure 2 is this path that you're taking as you ski down the hill. I'm asking you to visualize it. Figure 3, I'm projecting that plot down to 1 dimension, 2 dimensions. Okay. Exercise 2. Exercise 2, very inefficient way to solve a system of linear equations, unless it's extremely huge. But you could use gradient descent to solve a system of linear equations. so this is what we look at in exercise 2. Exercise 2, we have a system of linear equations described by ax equals b. So this is your typical linear system of equations. So I won't write this out, because if you're in supervised learning, you've already seen this written out. I'm sorry if you're in another class and you haven't seen it, but that's why supervised learning is a partial prerequisite for this course. Okay. So this is our linear system of equations. Suppose we want to find a solution. Well, what we'll do is, for any given potential solution x, we can associate an error with it. The error will be, if this thing summed to 0, we would have solved the set of equations ax equals b. If we subtract b from it, we'll have some vector of errors. We'll square that vector of errors. And now this will give us a nice surface in terms of x parameterized by a and b, which is kind of a beautiful quadratic bool, which you can then use gradient descent on, for instance, to solve. So what I'll ask you to do is to write code now to solve such a linear system of equations with gradient descent. The tricky part of this, in part A, is though I ask you to solve it for a specific problem, you should make your code work for generic matrix A and a generic vector B. So somehow what you have to figure out, if you're going to do gradient descent, you'll need to take some time and calculate what the gradient of this is with respect to x, so that you can implement it. If you've never done this before, I suggest you do it by hand, and then you try to simplify it back into kind of a matrix equation. Okay, so that's A. B is the equations I asked you to solve with gradient descent. C, I asked you to produce a visualization as before. Okay, finally, there's problem 3. There's only, I think, 2 sets of challenge questions so far this year on homework assignments. Challenge means it's a coursework only course. This question has some very hard parts to it. Don't spend too long if you're making no progress on C and D. It's quite hard, but you know, but these are interesting, challenging problems, and this gives me an idea of what skills you have when you come into the course. Okay, so what is problem 3? Problem 3, in the end, is basically asking you to think a little bit about gradient descent in a more abstract setting. What problem 3 is involved with is the following question. Suppose we have a function in one dimension, okay? So it's just the single dimensional case. We're going to do gradient descent with a fixed step size. A and B, which shouldn't be too bad, basically ask you to, well, if you do gradient descent with a fixed step size and you start at some point, will your solution converge, i.e. will it eventually make it to the minimum after an infinite number of steps, or will it never converge? Okay. Now, one way to do this is, to provide some experimental evidence that it converges. Even stronger is to kind of give a mathematical argument that it must converge. But you can get credit either way for A and B. So basically, we're asking, is there some non-trivial starting point and step size such that it converges? What do I mean by non-trivial? Well, clearly if you start at the solution, it converges. Likewise, if you choose a point so that the first step puts it exactly at the solution, it's trivial. Okay, so we're asking, for a generic x0 and a generic lambda over some range of values, does it converge? For part C, for part A and B, I asked you if there was a starting point x0 and a step size lambda such that it converges. Now I ask a slightly different question. In part C, I ask the question, for what values of lambda does there exist a starting point such that it converges to 0? Okay? So what range of lambda will this converge for? And remember, the natural way many people think about gradient descent is to keep using a decreasing step size, but this is not what the question is asking. This is asking if you have a fixed step size. D, there's many possible correct answers, but in D, basically ask you to think about gradient descent in one dimension and ask you to formulate a set of sufficient conditions for it to converge in one variable. Okay. Questions about the first coursework? Okay, well, you'll have a chance to ask questions to me or the lab assistants during the lab, and likewise, you'll be able to email the course mailing list questions. Okay. Coursework 2. Who here is either knows Latin or is familiar with Occam's razor? Are any of those hands knows Latin? Okay, so what's Occam's razor, more or less?
The simplest solution is usually the correct one.
What?
The simplest solution is usually the correct one.
Yeah, so this is kind of a big, people in machine learning love this phrase because it kind of fits with a certain ideology of a way to solve a batch of machine learning type problems where, often we have some problem, we want to fit data to it, and the idea is that somehow we want to fit data, but not with too complex a solution, because perhaps with the complex solution, we're fitting noise. And that somehow a simpler solution is better, but in machine learning, maybe it gets quantified a little bit. Somehow we want to trade off with the noisiness of the fit and the complexity of the solution. In this problem, in this coursework, well, we'll get to see some instances of this. Okay, let me describe at a high level and then go into more detail. This coursework is about linear regression with basis functions. For those of you in supervised learning, Massey will probably touch on basis functions next week, but he'll certainly immediately generalize it to kernels in his lecture. But this is linear regression with basis functions, and if you go down to figure 1, you'll see what I mean. So here in figure 1, we have 4 points. We have a point at 1, 3, 2, 2, 3, 0, and 4, 5. Now you can imagine fitting these with various curves. For instance, we've fitted it with this curvy line with the cubic equation. We've fitted it with a straight line plus an offset from the origin. Also, this is often called polynomial regression. Okay, so what exercises 1 will be about is basically exercise 1 will just ask you to do polynomial regression, fit a constant, the best constant that fits it, the best linear, the best quadratic, the best cubic function that fits it using least squares with basis functions. Problem 2 extends the setting a little bit. If you look at this picture here, see this picture with these two lumps, this is essentially sine squared. Here what I ask you to do is, well, the first thing you're going to do is generate some random points about this curve. So you get a data set like in the figure. This is exercise B. Then I ask you to fit, using polynomial regression, fit this curve. Exercise C, I ask you to plot the training error relative to the dimension. So what do I mean by the training error? Okay, so the training error, so I'm going to keep it at a high level and go into the details. I ask you to fit the training error. So the general intuition is that the higher the degree polynomial, the closer you can fit the data. So you're going to expect the training error to go down. Okay? But of course, when you start fitting with very high degree polynomials, because you're working on a computer with fixed floating points, there will be some accuracy issues. Part D, I then ask you to, with these curves you've generated, generate another independent set of data from the same distribution, and then plot the testing error. See how well those curves predict for the new values. Then in part E, I ask you to smooth out your plots by running this over and over and over and averaging your results. In part 3, rather than a polynomial basis, ask you to do it with a basis of sine functions with ever decreasing periods. Okay. Okay. So this is the overview of what is to be attempted in exercise B. Let me go through the mathematical background quickly. Some of this you're going to have to think through. So we have a data set of points. This is an equation 1. X's are vectors in Rn. You're going to have some L points. The sum of squared errors is a measurement of some predictor. So if you find some vector W, the sum of squared errors with respect to W is just equation 2, where W dot xt is the dot product. Okay. 3, I discuss how X can be expressed in matrix form. Then we put the sum of squared errors in matrix form. Then in the following paragraph, through equations 4 and 5, discuss what it means to use basis functions to create a feature map. Okay? So phi is our feature map. And the basic idea of using basis functions is you take your original data set and you transform your data set to potentially higher dimension and potentially lower dimension by using a number of basis functions. Then, so you transform your X matrix into a matrix based on the feature mapping in equation 5. Then finally in equation 6, you then do, instead of doing linear regression where your data matrix is X, you do linear regression on the phi matrix, and that gives you your coefficients for the function that will predict in that dimension. Okay. Questions? Okay. If there are no more questions, let's go over to the lab and start Matlab. Now there's going to be 2 rooms. Unfortunately, there's so many people. If you're confident in your programming skills, you should go into the room where I won't be speaking, which will be 120. I'll be speaking in 105, and either work on Mathematica with help from the tutors independently, or work on the first coursework. Okay? So let's go ahead and change rooms now.